So I hope you found the brief lecture on Friday interesting by Pasquale. I mean, he showed you a lot of what we do in terms of numerical combustion. There's a very big, not huge, but I mean a very large community of combustion scientists that are dealing specifically with numerical simulations, and they have become increasingly important, although it is extremely difficult, okay, to simulate reactive flows in general, especially for large systems like combustion chambers. The interaction, for example, of the combustion chambers with turbo machinery, for example, is a very complicated issue. Rocket engines are extremely large. The Reynolds numbers are huge. So there is a lot of what we call subgrid modeling, in that we cannot simulate all of the scales involved, as Pasquale told you. And sometimes they can be not fully reliable, these simulations, but they can be extremely important, especially if it is impossible to build, okay, a prototype. Okay, so what we do first of all is some, let's say, parametric analysis, okay, on with using numerical simulations. Okay, there's a variety of things that you can be studying, okay, in several, let's say, configurations. And this is what we're going to start to look at today. So let me just write part 3 here. Well, so we did a part 1, thermodynamics or thermostatics, a part 2, which was non-equilibrium, okay, homogeneous systems, reactive systems, so chemical kinetics. And now we are dealing with part 3, okay? Part 3 is essentially reactive flows, okay? And this is the actual sort of important word here, flow, okay? We're going to essentially try and understand what we mean by reactive flow in general. So the logic of the course, so we're going to obviously start from the very beginning. So we're not going to deal with extremely complex things that we saw on Friday. Clearly, we won't have time, for example, to talk about turbulence. But really, if you've done some fluid dynamics and some notion of turbulence, the two things can be sort of added rigidly together. So a reactive flow plus turbulence will actually give you a turbulent reactive flow, and then that is what you usually have in a combustion chamber, okay? But before you study turbulent reactive flow, which is the sort of the arrival point, okay, the end of the story, you have to learn about laminar reactive flows, okay, so very much simpler reactive flows, and the kind of really basic solutions that you can have for these kind of things, okay? So this is what we're going to introduce today. Before we do that, clearly, we have to understand what we mean essentially by a reactive flow in itself, okay? I'll give you sort of a spoiler. We're going to be dealing essentially with 3 components, with 3 basic phenomena here. Well, one, you know, okay, it's the reaction part, okay? So we've done a lot of that in chemical kinetics. We've seen a lot of that. We know that it's an extremely nonlinear process that depends exponentially on temperature, okay, and it can have an explosive behavior, okay, either thermal explosion or chain branching explosion and so on. Okay, that we know. The two things that we'll introduce, okay, is so-called transport phenomena. Okay, we can write it here. Okay, by transport, essentially we mean the transport of quantities which can be associated to mass. So for example, the transport of molecules, okay, molecular concentration of a certain species. It could be temperature, okay. It could be momentum, okay. Things of this sort, energy, and things of this sort. So temperature and energy are related, obviously. At least temperature is a part, okay, of the total energy. Transport implies movement from one point to another. So what we're doing in actually part 3 is adding, okay, extra independent variables, which is essentially the variables that are related to space, okay, spatial variables. So in chemical kinetics, we added time, and we were dealing with ordinary differential equations, which describe the temporal evolution of phenomena. So clearly you had a spatial homogeneity there. So you had the same phenomena happening in every part of the space. So there was no space in effect. And now we're adding space, not just time, space. So we're going to be dealing with essentially non-stationary or transient phenomena that depend on time and space, okay? And obviously when we talk about space, we will be dealing with fields, okay, mathematical entities that depend on spatial coordinates. And therefore, if there is a variation in space, there are gradients, okay? So that's essentially a very short sort of introduction to what we're going to be looking at, okay? I hope you can sort of still hear me, okay? Okay, so when we look at essentially the very broad discussion of a reactive flow, we have to start with a so-called field, or okay? Let's concentrate with a scalar field, okay? So something that has only values, okay, in the real numbers, okay? So it's not a vector field, okay? So point by point, and at every instant, okay, you have a value. So the field is essentially something of this sort mathematically. So it's a function, a scalar function of time and of the space, or spatial coordinate here, x. So I'm going to just be dealing with, so this x is simply x, y, and z. Okay, I can put it here. Okay, T stands for transport. Clearly, this is generally a column vector. Okay, so what do we mean by that? Well, this could be, for example, the scalar field of density. So the density field rho, okay, of time and of space. So you can have a density that varies every instant, okay, so in time and in every point. So you can have like a gradient of density from one point to the other, okay? This could be temperature, okay? It could be, well, it could be concentration. So we can have, for example, for a species I, a scalar field represented by the mass fraction, okay? Again, as a function of time and of space, okay? So clearly, when we are dealing with something, or fields that are a function of time and of spatial dimensions. In general, the mathematical model that we're going to be looking at is not an ordinary differential equation anymore, but rather a partial differential equation, okay? Or PDE, okay? The Navier-Stokes equations are partial differential equations, okay? Nonlinear partial differential equations. Now, these scalar fields generally, okay, will be existing, okay, will be embedded, and they all coexist, by the way, okay? So they're like continuums or continua that coexist. So you have a density field, you have a temperature field, you have a concentration field, which coexist within a vector field, which we call the velocity field. So in this case, this is a little bit different in the sense that it has vectorial quantity values, okay? So I'm just adding here the vector v. So this fields will be, in some sense, and we'll see in what sense, sort of moved around, right, by the velocity field. Bear in mind, I haven't talked to you about single molecules, because in fact, we're going to be essentially concerned with something that is not concerned with the actual single molecule, okay? We are going to be looking at these abstractions, these sort of averaged fields, okay, that are the net result of a great number of particles. So for example, the temperature field, okay, if you look up closely, you're going to have a packet of extreme large number of molecules that have kinetic energy. We can sort of average out, okay, on a sufficiently large number of molecules, and then in that sort of general area there, we're going to give a value for the temperature at that point x and at that instant t, okay? So this is what we generally call a continuum. You have seen these in a large number of subjects. So you can have a solid, which is a solid continuum, or an elastic medium. You can have, in fluid dynamics and gas dynamics, you can have a fluid continuum, okay? So we've seen those. We're not going to be rigorously sort of redefining everything. What I'd like to concentrate a little bit is the concept of total derivative, which is very important. What do we mean by total derivative? Well, it's exactly what we mean. You can take any of those scalar field, for example. Let's take the generic the scalar field phi, and we want to know essentially the total derivative of phi with respect to time. How does phi, okay, vary with respect to time? Okay, and what does that mean necessarily? Because phi is a function of time, yes, but also a function of space. Okay, it's a field. What do we mean by the total derivative, okay, with respect to time? Well, I mean, look at how phi, the functional dependence of phi, well, it depends on, again, the time and space. So mathematically, okay, we know how to take this derivative, okay? It's essentially the partial derivative of phi with respect to time, okay? But clearly then there is another part, which is due to the dependence of phi from x, okay? Bear in mind that x, okay, it's not necessarily a fixed coordinate, okay? it could also be a trajectory, right? Something like this. So it could itself be a function of time, okay? Or it could be, for that matter, also a fixed point, for example, x naught, okay? But we have to generalize this, okay? So if we want to understand what this total derivative with respect to time is, we have to generalize, okay, the actual discourse, okay, to every possibility. So in this particular case, if we want to take the most general, okay, expression, well, then you'll have to consider, okay, the derivative of phi with respect to x, okay, which is nothing else but the gradient, okay, of phi, okay, which is a vector, okay, and then multiplied, so in this case it's a scalar product, with what? Well, with the derivative of x with respect to time. Okay, so you can see that we've just applied the chain rule, okay, the function of a function or whatever you want to call it, okay, the chain rule. let me put it here. So this is just a mathematical expression. It's the most general thing, okay? So in this case, for example, when all of these are non-zero, both d phi by dt and then the gradient and dx by dt, okay, what we're doing is we're essentially looking at the rate of change of the scalar field in time as we move along this trajectory x of t. Okay, let's make things a little simpler. Suppose that this trajectory is the simplest possible trajectory. It's a stationary point. So this is a constant, okay? What happens? So if it's a constant, we're just concentrating on one point. We're not moving around. And so the temporal derivative, d phi by dt, is essentially only d phi by dt plus the contribution, this term here, is clearly zero, okay? So the total derivative coincide, okay, with what we call the Eulerian derivative. Okay? So we're just fixing in one point, okay? And because phi is a field that essentially varies in time, okay? We're feeling this variation in time, okay? So if I want to, for example, have a pictorial sort of representation of this, consider your space, okay? So this could be a frame of reference, X and Y, something like that, okay? And now, how do we represent our field, X and T, or T of X? Well, usually a field in this 2D representation, you can represent it with isolines, for example. It could be a map. Phi could be an elevation, for example. It could be the surface, sort of how the elevation of a liquid surface, for example. Okay, so something like this. So you can have isolines. Okay, you can have, I don't know, a peak here. So what I'm drawing here is just isolines, okay, of phi. Okay. So every line is a value of phi. Okay. Now, and consider, for example, here, the point x0 that we used before over here. Okay. So this point, sorry, this field here, okay, phi is actually, you have to think of it as varying in time. So I've just taken a snapshot of this, but really think of it as something moving in time. So what I'm doing here, if I want to fix myself, okay, if I want to stay in a fixed point here, I'm just feeling the rate at which all these isolines are crossing my position, okay? And this is what this represents, okay? It's an Eulerian derivative, and it's non-zero simply because phi is a function of time, okay? But suppose there is another case. Suppose that phi of x and t is really non-dependent on time. What does that mean? It means that it's just a field that is only dependent on position, okay? So it's a fixed field. For example, it could be an elevation, okay? It could be an elevation in a map, okay? So these are two mountains, okay? And we're talking just about so every single isoline is the elevation, okay? Obviously, a mountain doesn't move in time, or well, it does in a very, very long sort of time frame. And so in the case that this doesn't move clearly, d phi by dt, if I stay in a single point, is identically zero. Nothing happens, obviously, right? On the other hand, okay, if I take the general definition here, I can also have that d phi by dt, the total derivative, is equal to, well, phi doesn't depend on time, so this first term is zero. The Eulerian sort of point representation is zero. And what we have here is simply the gradient of phi dotted with dx by dt. Now that's interesting. What does that mean? Well, it means that what I'm really doing, okay, is moving around, okay, this time. So suppose that I'm moving around, okay, in this case here, with a trajectory which is x of t. So I'm moving around at a certain speed, okay, dx by dt, and I'm crossing, if you can see, okay, these isolines, okay? So clearly, there are two reasons why phi should change in time, okay? I'm moving around, I'm running around, okay? And I'm crossing these lines. So the greater the slope, okay, the greater the gradient, okay, and the greater the rate of change, clearly. But also, the faster I move, so dx by dt, the greater the change. So it really is, let's say, a time derivative that depends on two factors: how steep my variation is and how fast I'm cutting these lines. Of course, look, if I'm moving along an isoline, okay, so I'm following this isoline here, okay, well, you see what happens. The gradient, okay, which is normal, the gradient is always this way, okay, and the trajectory, they're at right angles, and so this term will be zero, okay? So you see, if I'm running on a path that is actually at the same elevation, obviously the rate of change of the elevation is clearly zero. So you see that this is a concept that you've seen many times, okay, in previous courses. I'm just sort of reintroducing it graphically to give you an idea of what all the terms mean. Okay, so because usually you're given this definition. Okay, sometimes in a very sort of mathematical sense. So this is just a physical interpretation. Each of those two terms, okay, has a very, very clear interpretation. And in fact, it has an even more profound implication or interpretation if you look at fluid fields, okay? Why is that? Well, think about it. What happens in fluids? Well, X could in fact be the location of a fluid particle. Okay, let me write it here. Okay, before when I was talking about the elevation and maps and things of this sort, I wasn't concerned about fluids, but in general, when you have a scalar field that changes in time, the typical thing you'll end up thinking of is a fluid, right? Something that kind of moves continuously. So suppose that X is a location of a fluid particle. What does that mean? Well, it means that the way in which this moves, so the rate of change of this position here is in fact equal to the velocity field, okay? So this is the fluid velocity field, okay? So that kind of acquires an extra meaning, doesn't it? So let's well, I should have written here also X and T, okay? So so we're talking about a fluid, so we are talking about this scalar field, okay, phi, which could be, I don't know, the concentration of a species. It could be, again, the temperature, okay, of the fluid field, okay? Then the total derivative acquires a meaning. Now I'm going to give you a definition here, okay? Because we're talking about fluids, I want to really remember, I want to remind myself that I'm talking about a fluid. So I will use this notation here. The total derivative becomes what I call a material derivative. We call it here material. What does that mean? Well, the total derivative is essentially a general definition, okay? It could be of any scalar field, okay, in any circumstance. When I'm talking about fluids, okay, and I'm really following the trajectory of a fluid particle, then I'm talking about a material derivative. So this will be written as d phi by dt plus essentially the gradient, okay, dotted with dx by dt, okay, which is v, okay, the velocity field, okay. So it's a special kind of total derivative, okay, which is specialized, okay, for fluid dynamics, okay. Now I am, and we'll see why it's so important to actually have this definition, because I can really, from this definition, I can really write the conservation equations in a very, very sort of straightforward manner, okay? You can still hear me, right?
Sì, sì.
Okay, yes. So for some of you, this was boring. It's just a repetition. For some others, maybe it's not. So that's why I'm just sort of repeating these things. In fact, this trajectory, okay, for a fluid particle that moves, okay, with velocity v of the fluid flow, so it's being carried by the flow, is called a path line. okay? Path line in italiana, linea di flusso, okay, flusso. So don't confuse this with streamlines. Streamline has a different meaning, okay, linea di corrente. That's essentially a line that is always tangent, okay, to the velocity field, okay? So you have essentially a photograph of the velocity field. So you may have a grid, okay, and you have a velocity field like that. Can you give me just 1 second? I'll be right back. Sorry. Excuse me. So when you have a velocity field like that, streamlines are essentially lines that are tangent to the velocity field, okay? So it's not path lines. They coincide when you have a stationary velocity field, okay? Only then, okay? Otherwise, they're different. So again, when we are talking about a material derivative, this part, okay, of the variation has to do with a process which we can loosely call advection. Okay? So it exists because we're moving at velocity v, and we are essentially cutting isolines. Okay, so we are going through gradients of the velocity of the scalar field. Okay, so there is an Eulerian part, which is this one here, which has to do with the fact that if we stay in one point, we're feeling the variation in time of this scalar field, and then there is another part which has to do with how fast we're moving through the scalar field, and how steep, okay, and how sort of steep the variations are of the gradient itself. So clearly, if you have a completely uniform scalar field, the advection, even if you're moving very fast, okay, will be 0. Okay. On the other hand, if you have extremely large gradients and you're moving very slow, you're still experiencing a very large variation. Okay. So I hope this is clear, because it really has a lot of implications. Okay. And the reasons why d phi by dt can be large, okay, can depend on many aspects. Okay, it can depend on this term, it can depend on this term, or on this term. Okay, so this is a generalization, okay, of the reasons why a scalar field can vary in time. Okay, and it's extremely important. Maybe it's the most important definition or concept, okay, in fluid dynamics, that of material derivative. I'll give you an example of why it is important. Okay, suppose I'm concerned with the conservation, the principle of conservation of mass. Okay, it's a pretty sort of intuitive concept, in the sense that mass is not created nor destroyed. And at this point, we're not even concerned about chemical reactions, okay? For 1 minute. We're just considering a a fluid field, okay, composed of, say, air, which is non-reactive, okay, it's not reactive as far as we know, okay, and we're concerned with the fact that you cannot have essentially the disappearance or the creation of air, okay, from just nothing, okay? So this mass of air should be conserved, okay, in its motion, clearly, in its advection, okay, in its fluid motion. So the air can move with the wind, okay? So how do we represent that? Well, we can think of what we call a material, okay, surface. Again, whenever I use the word material, okay, I'm talking about something that moves, okay, with the fluid flow, the velocity of the fluid flow v. So we can have a material surface and we can have a material volume v of t. What does that mean? Well, it's an imaginary surface, okay, that actually is moving along with the particles, okay? So each point here of the surface has a velocity v of t. It's actually moving around with this is exactly the same velocity of the fluid flow, okay? So clearly, think about it. If this is a material volume or a material surface, okay, surrounding the material volume, okay, because each particle, okay, on the boundary is moving with the flow, there cannot be any net mass moving in or out of this material volume. So we always have to surround the same number of particles, right? Contain the same number of particles. So S is really containing, or V is actually containing always the same mass, right? So how do we express the mass, okay, of V? Well, it's the integral, okay, extended to this volume, okay, which again is a function of time, of the density times dV, right? That will be the mass in the material volume Vt. Okay? Well, very good. We have to say that this is constant. How do we say that? Well, we could say equals to a constant, or we could take the derivative of this and place it equal to 0, right? The time derivative. But clearly, not any time derivative. We have to consider the actual total derivative, which in fluid dynamics is the material derivative. So it's the material derivative of this integral, which is equal identically to 0. Okay? And this is the most compact way of expressing the conservation of mass. Okay? There is clearly no mass, no net mass through it. Clearly, if there were some net mass through it, then clearly this, as it moves, this derivative will be negative, for example, if it's losing mass or adding mass, okay? Also, think about this. Suppose that there are chemical reactions, okay, inside that. But chemical reactions don't create mass, okay? They just transform species from one to the other. But the net mass, okay, in kilograms is always the same. So again, that applies even if the flow is reactive, okay? So again, let me just specify here that V of T is a material volume, okay? And S of T is a material surface, okay? Again, composed of particles, S of T moving along with the flow, okay? So there is no net flow across it. Right, so now the only problem that we have, okay, so let me just put a big box here. So this is the conservation of mass. The only problem that we have here is, well, now that we have found a very elegant and very compact way of writing down the conservation of mass, well, we have to understand how, if there is, okay, a way of expressing the material derivative d in dt of an integral. Because remember, if I write it here, that whatever you're integrating it on a volume that depends on time. Okay? And so you can't really put this in here, can you? You cannot do that, because clearly the integral will be extended, okay, on a volume that really can change in time. And in fact, it does. Okay? So how do we do this? Well, we use, I'm not going to prove it or anything, but we use a very important theorem of fluid, which can be applied in, can be used in fluid dynamics, and has sort of can be employed in almost everywhere in fluid dynamics, which is the Reynolds theorem. Transport. Okay. Personally, it's a theorem that pops up in every single course that I teach, from aerospace propulsion to space propulsion, okay, to combustion. In fluid dynamics, you probably have seen it many times. It's a really important theorem because it allows us to express essentially this derivative here, the material derivative of an integral extended to a material volume. So suppose there is a generic quantity chi. Okay, this is a generic quantity. It could be a tensor, it could be a vector, it could be a scalar. Okay? At this point, it doesn't really matter. Okay? Of course, we'll be more interested in scalars, but oops. Now I have no idea what happened, but okay. Oh, there is an undo, but it doesn't work. Okay. Okay. So suppose that this is a scalar or a tensor, I mean, just a quantity, okay? A general quantity, clearly that depends on both x and t. So it's a field, okay? It could be a tensor, a vector, or a scalar field. The Reynolds theorem will give us an expression, okay, of the material derivative, okay, of the integral to the volume, the material volume, v of t. So that's why we're expressing it as a function of time, because it varies in time, of the quantity chi. Okay. So this, again, can be considered as the rate of change of chi, let's say, carried by the material volume v. Okay, so what we're monitoring is how fast, okay, the integral of chi on this material volume v is changing in time, okay, as it is being carried by this material volume. And the transport theorem, the Reynolds transport theorem, really expresses a very simple concept, okay? And that is the fact that as this material volume moves in time, what we can think of freezing it, okay? So you just freeze it for a second, for an instant, okay? And if you do freeze it, what you can do is you can think of this volume as being the frozen volume, okay? So it's not a function of time anymore. So what you can do actually is you can have a time derivative, because now you can put it inside, okay, the integral, because this is not a function of time anymore, of the quantity psi. So it's a sort of an Eulerian derivative, okay, extended to dv. But clearly, as we said, this cannot be the only term, okay? Otherwise, v would be fixed in time. So what you do have is an extra term which expresses now the flux, okay, of chi, of the quantity chi, through, okay, the volume, the frozen volume v. So what we do here, this is v, okay, and this is v, let's say v of t, okay. So at some point we freeze it, okay, and this would be v, this would be s, okay, the frozen surface, okay. And what we have here is the flux through s, okay. So chi of, well, how do you express the flux? Well, you have a velocity dotted, velocity field dotted with the normal, okay, on s. So that's the normal. ds. So what we're actually looking at here is a sort of flux. I can sort of maybe represented like this, but I don't know how sort of clear this picture would be. So let's see what this term here is. So this is the rate of change of chi in the frozen volume. And this would be the flux, okay? Okay, across S, okay? Now, clearly, both S and V are frozen. So clearly, what this means essentially is that when you're following, okay, the rate of change of a certain quantity extended to a material volume which moves, well, clearly, this cannot be equal to the Eulerian part is only, because if we fix, we take a snapshot and we fix the volume, clearly, the volume, the material volume is still going to be moving, okay? So what you can do, what you can imagine is you could freeze it, but then you also have to take into consideration the flux that is getting out of the frozen volume, because clearly the material volumes keeps on moving, okay? So again, the material and the Eulerian, okay, this term here and the Eulerian derivative, okay, differ by essentially the flux, okay? The flux across the surface S, okay? You've also, I don't know if you still prove this rigorously. I remember at my time, many years ago, we had to also give a mathematical proof of this. But what I believe is extremely important is to really understand the physical significance of this theorem, okay? And it's also quite, well, it's incredibly useful because why? Well, because clearly this is a very compact way of expressing a physical process, such as, for example, I'll just repeat it here, the conservation of mass. Okay, so let's go back to now our scalar field rho. This is the conservation of mass. I can write it in just, you know, as compact as this. Okay, it's a very, very compact way of writing it. But if I don't have a way of expressing that derivative of this integral, it's kind of useless, okay? But now look, I can really write this integral, this material, this derivative of this material integral as two terms, okay, using the Reynolds theorem. The Eulerian, okay, derivative extended to the frozen volume V, so d rho by dt in dV, plus, okay, the flux across the frozen surface S, okay, which is, again, rho, I'm just copying it from here, V dot N ds. Now, clearly, bear in mind that you have to always use the normal component, because clearly, if you have the surface S and the velocity somehow is tangent, okay, this is the normal, and the velocity is tangent to S, so it's at 90 degrees with the normal, clearly there is no flux across S, so this term has to be 0. I hope you see this, okay? Now, well, that's now much more tractable, mathematically tractable expression. Again, this is 0. Okay, I'm just repeating it here. Excuse me. So how can we treat this? Well, let me try and turn this surface integral into a volume integral. If you remember, there's something called a divergence theorem. I'm just repeating this term here. And divergence theorem really tells me that this surface integral can be expressed as a volume integral, okay? Again, the volume V is that enclosed by the surface S, okay, of the divergence, okay, of rho V in dV. So this goes to here through the divergence theorem, which we have to be familiar with, okay? And now look, we have an expression, okay, which is on these, it's two expressions, both integrated over volume V, and therefore it means that the integrand has to be 0. So all we do now is we have taken this and transformed it into a very familiar equation, which is the conservation of mass, okay? Which is in this form here. This can be manipulated, for example, like this. Okay, this is still a derivative of a product. So what you can do here is write V dot gradient of rho, okay, equals, we'll put it on the other side, minus rho divergence of V. Okay. This is a dot product. Okay. Let me just specify it here. Dot. Okay. Divergence. Okay, it's another way of writing it. In fact, remember the definition, okay, of material derivative. Isn't this the material derivative of rho? Yes, it is. Okay. So you see how we can write this as divergence of the velocity equals 1 minus 1 over rho d rho by dt. Okay, that's another way of writing it. Okay. So you may be familiar with the fact that incompressible flows, generally or loosely speaking, are flows that have constant density, okay? So the density is constant, okay? And if it is, so it's constant and uniform throughout your fluid field, then by definition, the material derivative is zero, right? So we have that the velocity has this property of being so-called solenoidal. It means that the divergence of the velocity field is zero. So this is a particular case of a vector field that has this property throughout, okay? It essentially has no sources, for example, of velocity, okay? And has this particular property here. So you can think of, you can look up examples of divergence-free, okay, velocity fields. And this is a typical thing of incompressible flow, okay, that it has to have a velocity field that is divergence-free. Okay, the divergence of the velocity is always zero. Otherwise, okay, you are bound to have variations of density, okay, in the material sense, okay, in this material sense. Now, in combustion, things are a little weird because there is sort of a confusion. Now, I may be confusing myself here on the concept of constant density. Now, fluid dynamicists in general are concerned with, all the time concerned with incompressible flows, okay? And generally speaking, an incompressible flow is a flow that has constant density and that essentially has the property that there is no variation of density through variations of pressure. What does that mean? For example, a liquid is like that, okay? It is very, very hard to change its volume, right? So the density will stay the same, okay? Even though you can change the pressure. Or another example of that is air, which generally is quite compressible. But if air, like atmospheric conditions, okay, is very slow, and by slow I mean at a Mach number, okay, that is quite low, then you can assume that the fluid velocity is extremely smaller than the velocity of sound, okay, in air. And that means essentially that there are no variations of density as a result of variations of pressure, okay? There will be variations of velocity due to variations of gradients of pressure, clearly, but no variation of density. Now, that's not the case when the Mach number is very high, or it's close to 1, let's say. Okay, in that case, you can have a shock wave, for example, and that's a typical result of your density being increasing by a sort of as a result of an increase of pressure. Okay. In combustion, things are a little weird because you can have very slow flows, like very slow flows, meaning very low Mach number flows. So the Mach number is extremely low, almost zero, but you can still have huge variations of density. Now, why do you have that? Well, you have it not because of pressure, but because of because of temperature. Okay, so across a flame, for example, if we create like a exothermic reaction somewhere, well, you know that the temperature will rise, okay, and the density will decrease, but the pressure will almost stay the same. We're going to prove that quite rigorously later on. But again, it's good practice to start looking at the various kinds of flows, okay, that you can have. There is sometimes a kind of confusion about the word incompressible, okay? Because some people say, well, it's incompressible if the speed is very low. But clearly in combustion, that kind of is not totally true, because the speed can be very, very low in combustion, okay? You can have a very, very sort of slowly evolving fluid field, but still have huge variations of density. So you have to remember, okay, that one thing is the variation of density through variations of pressure. You can have, for example, acoustic waves propagating, okay? So that is sort of, let's say, an elastic aspect, okay, of your fluid flow, okay? And that usually are things that become important at very high speed, when you have essentially either acoustic waves that you want to study, or, for example, when you have an acoustic waves obviously travel at the speed of sound, and or when the velocity itself is very large. At that point, you have sort of these gas dynamic solutions such as shock waves. But in combustion, it's really something else. Okay, in combustion, you can have very, very slow. You can have no acoustic waves. You can have very, very slow fields. Okay, evolving fields, but still have a huge density variation, and that will be a density variation which is not caused by changes in pressure. It's caused by changes in temperature. Okay. So clearly, when you light it, when you have a hot pocket of air, this will be, by buoyancy, it will go up, clearly, because it's less dense. Okay, and this is what happens in combustion. So in combustion in general, the divergence of V will be different from zero, simply because this term here, okay, will not be zero at all. Okay, but anyway. Again, for those of you who have done a little bit more of gas dynamics, I suggest that you start looking, okay, at the various kinds of fluid dynamics that you've seen, okay, and try to sort of put each phenomena in the right kind of cassetto, in the right drawer, okay. Let's go back to essentially this formulation here, which is the most general possible expression of the conservation of energy in fluid dynamics, okay? As you can see, well, this is the conservation of mass, okay? And so the total mass, but we can actually conserve anything, okay? So suppose you have a scalar field, phi, okay? This in general could be, for example, it could be a single species in a multi-species system, okay, where you have many species, many reactions between the species. You want to conserve that. Let's see what that could mean. Well, what we write is exactly the same thing, okay? There is an Eulerian derivative, and then what we have is the divergence of essentially a flux, okay? And we can generalize this by, so this would be a flux, okay? Which we can generalize as just F, okay? Now equals to, well, if it's completely conserved, then it's a sort of a passive scalar, okay? Nothing happens to it, okay? So if I'm putting the certain quantity of phi, it could be, for example, a color in a liquid, okay? An ink in a liquid. That will be conserved, okay? It could be more or less dense because it expands, okay, throughout the liquid, but it won't be destroyed or it won't be created. However, if you're talking about a certain species, H2O, for example, in a chemical reaction, well, you can add a source term here. For example, G, that would be a source term, okay? And that is essentially, for example, in combustion, what the role of chemical reactions, okay? okay, is, okay? Adding certain species or subtracting certain species. Now, clearly, the total mass will be conserved, okay? So that is a source term that for a species will be a chemical source term, okay? Now, you can also look at the units here. Whatever units phi has, this would be the units of phi, and then seconds to the -1 because you have a time here at the denominator, right? Now here, this operator here is a gradient. I mean, it's a derivative operator, so it's d by dx. So this would be 1, okay, over a meter, so a meter to the -1. Okay, so the flux is essentially whatever units of phi is, okay, seconds to the -1, and then times meter, okay? And again, the source term will be this times seconds to the -1, okay? So again, as I said, for species conservation, okay, we can consider phi as being, for example, the mass concentration, rho I, okay? That's why it's so important to know all the sort of different ways of expressing the concept of concentration, okay? And we're going to write very soon a general conservation equation for a single species, I, okay? So how do we write this? Well, this is a little bit tricky as a concept because in general, in fluid dynamics, you're not really interested in having many species, right? Many chemical or molecular species. You're just considering a fluid as being composed of one kind of particle, okay? Or if you will, rigid spheres, particle as rigid spheres, they move around, okay? I can consider them as being carriers, okay, of quantities like temperature, like density, and so on and so forth, okay? Now, in combustion, clearly, we're dealing with species, chemical reactions, and so we need to actually concentrate on the notion of a concentration field. So for each species, so suppose I'm counting I, okay, I'm considering, I don't know, 1, 2, 3, 4. Remember that I was doing some kind of ordering, okay, at the beginning of the course when I was interested in chemical equilibrium. I can use the same numbering here, 1, 2, 3, 4, for species such as hydrogen, oxygen, I don't know, methane, water, and so on. For each of those, I will have to write down a conservation equation of some sort, which has this kind of general form, okay? Why is it tricky? Because, well, we're considering a number of different continuums, okay? So one for hydrogen, one for oxygen, one for CH4, not CH2, H2O, and so on. So you have to think of those as being superimposed one on the other. So they're sort of penetrating continuums, okay? Each molecule is different, okay? And they all coexist, okay? So on a continuum mechanics kind of approach, we have to consider not just one, but n, okay, continuums, okay, being superimposed one on the other or penetrating into each other, okay? They coexist, okay? So I could think of, now you could sort of magically separate them into the H2O continuum, into the CH4 continuum. Clearly, if it were completely homogeneous, we would have partial pressures, right? Exactly like we did when we created the mixture, okay? Now, clearly, this is far more complicated because it's not just creating a mixture which is totally homogeneous, okay? But we're actually looking at continuums that are time and space evolving. So they're spatially evolving, they have gradients, okay? And they're evolving in time as well. So it's much more complicated. It's completely non-equilibrium, okay? So in order to do that, because we have all these continuums, we have to differentiate them, okay? And so the most general representation of that is if we consider each of those continuums, referring to each species, as having its own velocity. Okay, so we introduce the velocity field VI, okay, of the ith species. Okay, so we have essentially a scalar field rho I for x. Okay, I don't know why I can't. Well, that's an I. Okay, this is our. You can still hear me, right? You haven't fainted or anything.
No, si sente.
Okay. So for each species, we have a scalar concentration. Okay, scalar field rho I of x and t. Okay, that's my ith. Okay, continuum. Okay, and associated to this continuum, there is a velocity field. Let me write it in a better way here because I want to separate the dot from the I. Okay. So there is a velocity field associated to this scalar field. Okay. Clearly, if we only had species I, only just one species, then it wouldn't make sense, right? To distinguish between the velocity field and the velocity field of that species, okay? Related to that species. It would be the same concept, okay? But then what is the velocity field? What is the sort of the overall velocity? Well, again, there will be a difference. So we are considering essentially a velocity field VI and then a so-called bulk velocity field, or bulk velocity, not velocity field, which we call V. Okay. Now, what that is a little bit at this point not clear, because if we have n continuums, each with its own velocity, then how do you define the bulk velocity? It's sort of an average velocity. Well, we'll see that there are several ways of defining it. Okay, not too difficult. It's an average, and there are many ways in which you can take the average. Okay, so that's the bulk velocity. That's the velocity field. The interesting aspect is that these two are not equal. They don't coincide. So VI minus V is different from zero. Now, this is a sort of a relative velocity if you think about it. The ith species as a continuum can locally move faster or slower than the average velocity. That is what we call diffusion velocity. Diffusion velocity, and we'll indicate it with a big V, sort of a capital V, and it's still associated to species I. So it's a relative, it's called diffusion velocity. And what it is, it's a relative velocity of the continuum I, okay, with respect to the bulk or average velocity v. Okay? So it's a sort of a relative velocity. So this is the tricky part when you have a multi-component system, is that you don't have one definition of velocity, you have n. And because you have an overall velocity, sort of an average velocity, there's also this additional thing that's going on, okay? Which is this relative movement between the continuum I, okay, and the bulk convective overall velocity, which gives rise to a new aspect or a new phenomenon, which is the diffusion. So it's a sort of a motion or transport of the species with respect to essentially the average, okay, motion of the whole continuum seen as a whole, okay? And so, how do we write write our conservation, okay, equation? Well, remember, let's go back here, okay? Remember the general form of the conservation equation. So now we want to write the conservation equation for species I. So phi now becomes our concentration, for example, the mass concentration. What about F, the flux? Well, the flux can be expressed as rho I, okay, times the velocity. But what velocity? Well, vi, the ith, okay, velocity, the velocity of the ith component, so that we can write down something like d rho I by dt plus the divergence of rho I vi, okay, equals some source term. Now, what would be the source term for species I? Well, we know what the source term is, okay? It's omega I, okay? It's the rate, it's the reaction rate, not the reaction rate, it's the, sorry, the rate of production or destruction of species I in every point and at every instant, okay? So this would be also a function of, omega I, a function of space and time, okay? And clearly what this is the result of many reactions, okay, involving species I, all of the reactions involving the species I. So this is how you you write it. But again, we don't really know what this VI is. So let's substitute the fact that VI is actually a diffusion velocity, okay, which we haven't defined yet. We haven't defined anything yet, if you think about it, and a bulk velocity, okay? And so you'll see that essentially the conservation equation for species I can be written as d rho I by dt. Then this term here, which is the divergence of rho I times the diffusive velocity, okay, which has to do with a relative motion of species I with respect to the bulk, okay? And then the divergence of rho I and V, okay? And this has to do with essentially a bulk kind of motion or an average motion, okay? Equal to omega I. So you see that when we're concerned with reactive flow, okay, we have to take into consideration, okay, the fact that the flow is multi-species, okay? So it involves many species. We have to take each one, and for each one, write down a conservation equation. And if you look at each conservation equation, what really pops out is that you have essentially three things going on. So three fundamental phenomena. Well, you have this term here, okay, which deals with what we call diffusion. Okay, it's the diffusive flux, rho I V I, where V is the big V. Okay, it's a diffusive flux in the sense that it takes into consideration, okay, the flux that is relative with respect to the bulk. It could be zero, okay, if species I moves exactly like the bulk, but it could also be non-zero if it doesn't, okay? There is some difference, and we'll see the origin of that, okay? We will have, it's triggered by gradients in concentrations, okay? And the fact that you have zones where this could be moving, everything could be moving with velocity v, but you could also have a situation where you have a complete stationary flow, okay? A quiescent flow. In this case, this term will be zero. And this term, we know what it's called convection. Use it interchangeably with advection, okay? And it has to do with the bulk movement, okay, of the species I. But imagine that term is zero, V is zero, okay? Then what happens? Well, you can still have some motion. You can still have some transport of species I moving. Why? We'll see very soon, due to something called Fick's law, that there can be a velocity field associated to species I, even if the bulk flow is zero. So you have a completely motionless system. Imagine being in a room where there is no wind, there is no bulk flow of anything. You're in a laboratory and everything is kept quiet and kept stationary. You can still have a bowl of smoke, okay? It's not going to stay there. You can produce it in any way you want, as long as you keep it very, very sort of smooth, okay? You can smoke a cigarette, for example, and have a puff of smoke. Don't do that. Bad for your health. But imagine, okay? There is a high concentration of smoke. Smoke is a bad example because it's really solid particles to some extent, but a lot of it is, well, the smoke of the cigarette is mostly gas, okay? Suppose it's a gaseous species. This will have a high concentration. Around it, it will be very low concentration. So there is a gradient, okay, of composition or concentration, sorry, of the smoke. As it turns out, when you have gradients, we'll define it next time, but when you have gradients of concentration, you also have a velocity field. You have a transport of smoke, so of concentration from higher areas of concentration to lower area of concentration, okay? And this, in fact, is related to some extent also to the fact that the creation of a uniform mixture, if you remember the very first part of the course, is spontaneous. So it's in the direction of a growing entropy, okay? And so equilibrium really, thermodynamic equilibrium is really when it's reached when all these smoke particles will be uniformly distributed around, okay? So that's where our arrow of time is actually moving towards, okay? So you're starting from a non-equilibrium, okay, configuration, and you're going towards equilibrium. What we're doing here is really studying the evolution of non-equilibrium configurations, okay? So that's what we're actually doing. So look at these three terms: diffusion, okay, convection, and again, reaction. That's what the bottom line of reactive flow really is the interplay of these three terms. And these three terms in each single point will cause a variation, here it is, of concentration in time. So if I take a probe and I place it in a fixed point, okay, the concentration of a species can be changed as a result of reaction, as a result of convection, and as a result of diffusion, and the interplay of these three things happening at the same time. Okay? In fact, suppose we are in a steady state. What does it mean? What does steady state mean? It means that at some point, I don't have this term anymore. Okay? So it means that whenever I put my probe, the concentration is constant. Well, then what this equation really is telling us is that there is a balance between diffusion, convection, and reaction. They balance out. If, for example, there is no reaction, okay, there is going to be a balance between diffusion and convection, okay? If there's no convection, well, we'll see. and there is only reaction and diffusion. There is a balance between diffusion and reaction, okay? This is quite interesting because, in fact, that's what happens in what we are used to be calling flames, okay? Flames are basic solutions, okay? They can be steady state solutions of reactive flow. So imagine if you have a lighter, you light the lighter, look at it, okay? If nothing is turbulent, so if you keep everything quiet, you're going to have, okay, within the lighter, a sort of very strange kind of solution like that. With, if you notice, there's some yellow color here, there's some bluish color here, okay? I'm just essentially drawing the flame out of a lighter. Even better, if you have a candle, okay, like this, you may have noticed this kind of, well, I've done it a little bit, okay, badly, but the solution, okay, which can be kept at steady state, okay? Sometimes it flickers, it goes up and down. If I move the air around, it will kind of move because it will be subject to some convection. But really, in a laboratory frame, it can be kept at steady state. So if I place myself here, my probe here, or here, or here, okay, this derivative in time will be zero identically. So I know that in there is a balance between diffusion, convection, and reaction. Okay. This is, well, we ran out of time, but this is a classical solution called, in fact, a diffusive flame. Okay, a flame that essentially is kept in steady state by essentially diffusion. In fact, convection may even be completely absent in a candle flame. And I'll challenge you with this. Well, why do you think you have a convective flow here? in a candle? Well, if you keep everything completely motionless, the only reason why you could set the bulk of the fluid in motion, well, think about it, is through buoyancy, right? The fact that you're heating up air, okay, in general, the fluid, okay, and this expands, it decreases in density, and locally it will tend to float. By floating it, there will be some entrainment from the sides, okay, and you have a sort of a convective, okay, a natural kind of convection, okay. Natural because it's not driven from outside, okay. It's just naturally occurring because there's a hot reaction. But where can we get rid of that? Well, if we take the candle on the International Space Station, there is no gravity, there is no buoyancy. And so there is no convective flow, okay? And so if there's no convective flow, this term goes to zero. So we are to expect that there's only a balance between diffusion and reaction, and therefore, we're to expect that the shape of that candle will change. And in fact, if you do take the candle on the space station, you'll be surprised what happens. What happens? This is your candle, and the flame will have a perfectly spherical shape like this. It will also change color, and I'll show you later on, okay? That's just a sign of the fact that we've gotten rid of one of the three terms, and so we have to expect that the solution is, well, it's a solution of a different equation where that term, convective term, is not there, and therefore we are left with a different solution, which is perfectly spherical. Okay, that's enough for today, and we'll continue this next time. Okay, I'll stop recording.